Hello, everyone. I wanted to take a few minutes to derive the relativistic addition of velocities formula. We had started that in class, and I told my students I'd finish it later for them, so I'm going to do that now. Let me turn on my document cam. So if we have two reference frames, let's say frame S, and then let's say we have, this is the x-axis, this is the y-axis, and we have moving alongside of it in such a way that the origins were at the same location at t equals 0, then we have x prime, y prime here, and we'll assume this is moving with velocity v, and this would be frame s prime. Okay, if you come over here and say this is an x prime, then you'd see that this distance right here is v times t, and then of course this distance would be just the x prime. So the x would actually equal x plus v, or x prime plus vt. So that's the general scenario to get the Galilean transformation, but the Lorentzian transformations are slightly different. Specifically, the x prime plus vt prime, excuse me, that should have been prime, the x prime plus vt prime are actually the same. Of course, in Galilean, there's no difference in time. That's why I didn't have the prime there, but now I'm going to. So in the Lorentzian transformations, we get that x is equal to not only x prime plus vt prime, of course, like I said, in Galilean relativity, t and t prime are the same, but it also includes this gamma factor where gamma is defined to be 1 over the square root 1 minus v over c quantity squared. In this frame, y is equal to y prime, no difference there because there's no motion parallel to the y-axis, and of course z would be pointing out of the page, and that's perpendicular to the motion as well, so we get z is equal to z prime. The other weird thing is time, which will have a gamma just like we did on the x before, and there is going to be a t prime, but here's the inner commingling, if you will, of space. So to actually account for what we observe, we actually have to have v times x prime over c squared. All these things, of course, allow for the invariant hyperbola, or the basically speed times proper time, that sort of thing. Now we can use these expressions to derive the x component of velocity u as well as the x prime component of velocity u and stuff like that as follows. So let's start off with u sub x. So this is a velocity measured in the x in the s coordinate system, but along the x-axis, in other words, parallel to the x-axis. So that should be dx over dt, but you see your x is a function of x prime and t prime, so we probably want to use a chain rule to make that dx over dt prime times dt prime over dt. Of course, we have t as a function of t prime, but not t prime as a function of t, so it might be better to divide by this thing and, of course, flip it over. So we end up getting dx over dt prime divided by dt over dt prime. So let's handle this dx over dt prime first. So dx over dt prime is equal to, I'm taking the derivative of this with respect to t prime. Obviously, the gamma is just a constant because it only depends on v and c and square roots and blah, 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 right? But when we hit this other term, we get dx prime over dt prime, which is the very definition of u sub x prime, plus v times dt prime is just going to be v. dt prime, on the other hand, or dt over dt prime, by the way, I don't know why I left that prime symbol off over there, that's going to be equal to, again, I get a gamma that I pull out in front, I'll get dt prime over dt prime, which of course is just 1, and then I'll get plus v over c squared times dx prime over dt. dt prime that is. And that, of course, is u sub x prime again. So now I can write u sub x is just this divided by that. Notice the gamma is going to cancel out. This is going to be 1, and I'll get, and this is ux prime, so I'll get ux prime plus v, which is our normal Galilean formula for addition of velocities. But here's the part that's not normal. 1 plus, here's the ux prime again. So I'll say u sub x prime v over c squared. So a velocity in the x direction of u sub x will result in velocity equal to u sub x prime plus v over 1 plus u sub x prime v over c squared. That factor is actually going to work out for us to always asymptotically approach c. So even when you add, 99% of the speed of light to 99% of the speed of light, you're still going to get something smaller than the speed of light. It's a very neat function that happens to work out this way. That's not all. What if we have, for instance, a velocity in the y direction? So then we have, say, u sub y is equal to dy over dt. But again, we've got y prime, and generally the x's are in terms of primes, so we really want to do that chain rule thing again. We're going to say it's dy over dt prime times dt prime over dt. But again, we have t in terms of t prime, not t prime in terms of t, so I'm going to call that dy over dt prime divided by dt over dt prime, which we've already worked out. And of course, we know dy over dt prime is just going to be dy prime over dt prime. So I can finally say dy prime over dt prime over dt over dt prime. So that's just uy prime. And this, of course, is the same thing it was before, which was a gamma times 1 plus v squared over c squared times ux prime. So we can put all that together and we'll see that uy now becomes uy prime from that part. The gamma that would be down at the bottom becomes the square root of 1 minus v squared over c squared. I'll write it like this, over c squared. And then the other part becomes 1 plus ux prime v over c squared. So that's uy prime. As you can probably guess, the uz is going to be the same thing. uz is dz over dt, but that's going to be dz over dt prime times dt prime over dt, which is going to be dz over dt prime over dt over dt prime, which equals, of course, this z is equal to z prime, so that's just going to be dz prime over dt prime. This was supposed to be prime right here. I dropped it. Sorry about that. Divided by dt over dt prime. So you can see I'm going to get exactly the same result as I did before, except I'm going to have a uz prime there. So uz is just equal to uz prime times the square root 1 minus v over c quantity squared, all that over 1 plus ux prime v over c squared. And that is our derivation of the relativistic addition of velocities.